The objectives of this topic are find the domain of a function, combine functions using the algebra of functions specifying domains, form composite functions, determine domains for composite functions, write functions as compositions. If a function f does not model data or verbal conditions, its domain is the largest set of real numbers for which the value of f of x is a real number. Exclude from a function's domain real numbers that cause division by 0 and real numbers that result in an even root, such as a square root of a negative number. So even roots, we can't have negatives underneath. Fraction bars, we can't have 0 underneath. Otherwise, anything's fair game for the domain. So we take all real numbers and we subtract the real numbers that we can't have. We remove the real numbers we can't have. So find the domain of the function g of x equals 5x over x squared minus 49. We can't have 0 on the bottom of this thing. So x squared minus 49 cannot be equal to 0. Find the values that'll make it equal to 0. Set it equal to 0. Add 49 to both sides. X squared equals 49. Take the square root of both sides. X would equal plus or minus the square root of 49. X would equal plus or minus 7. We also could have factored x squared minus 49. X squared minus 49 is a difference of squares. It factors to x plus 7 times x minus 7. That's more proof that we would need the plus or minus. We would need them both. X plus 7 equals 0, x minus 7 equals 0, x equals negative 7, x equals positive 7. So we have to exclude those from the domain. So instead of negative infinity to infinity, we cut out negative 7. We cut out positive 7. And the way we cut those out are by using parentheses to indicate that the negative 7 is not included. So we're uninterrupted from negative infinity up to negative 7, but then we need to uninclude negative 7. We join that, we union that with negative 7 to 7, not including the negative 7 up to not including the 7. Not including the 7 means we close with parentheses. A square bracket would include it, a parentheses unincludes it. Then we union that, we join that with a final interval from that not including the 7 all the way up through infinity. And remember, negative infinity and positive infinity always take parentheses because the infinities are ideas. They are not actual numbers. If we would have had a function that is a square root, we would take what's underneath the square root and set it greater than or equal to 0 because it couldn't be negative. If we had a square root in the denominator of a function, for instance, this one that we're seeing, but instead of x squared minus 49, it was the square root of x squared minus 49, we would set the x squared minus 49 just greater than 0. We wouldn't bother with the equal to because we knew it couldn't be equal to because it was the denominator of a function. So those are the three things you're going to watch out for. Domain in a fraction looking thing like this, domain under an even root, and an even root on the bottom of a fraction looking thing. Let's start with some notation. We've heard of f of x. We've heard of g of x. Introducing f plus g of x. So why have I written f plus g in parentheses? Well, if I didn't, it would just be the letter f plus g of x. We're indicating that we want f plus g, and that's why the whole f plus g has to be in parentheses, because the letter f plus a function is what it would be without. And why is it important that we know that this is f plus g? Well, f plus g of x just means f of x plus g of x. F minus g of x. That one just means f of x minus g of x. F times g of x. Guess what that means? I don't think you can do it. Oh, crap, you did it. F of x times g of x, sure. This notation is telling us what to do to the functions by doing it to the function names, and it's staying a function by telling us that this is the name of the function of the variable x. Again, this doesn't mean f plus g times x, just like f of x doesn't mean f times x. It is a function named f that uses the variable x. This would be a function called f plus g. It is a function of x. What does it mean? Well, it's f plus g, f of x plus g of x. There's one more of these. I'm not going to write it down here. I'm going to give it its own space. You already know what it is. It's the one I didn't do. F over g of x. F over g. F divided by g. F of x divided by g of x. Now, when we say f of x divided by g of x, we are making a big assumption about g of x. I'm going to see if you can get there before I actually say it out loud, but I'm going to start hinting around it. G of x is on the bottom of a fraction. We're dividing by g. There's a certain thing we can't have on the bottom of fractions, and therefore it's a certain thing g of x can't equal. G of x, if we're expressing f over g, can't be 0 because we can't divide by 0. That makes this a restriction of this function. So let's say we had f of x equals 9x, g of x equals x plus 2. I'm going to keep them relatively simple right now. What would f plus g of x be? Well, we know that f plus g of x means f of x plus g of x. F of x is 9x plus g of x is x plus 2. So f plus g of x would be 10x plus 2. To get the addition function, we add the functions together. And adding functions is no different than adding polynomials or adding whatever they end up being. It's just a new notation that we're getting used to. We know how to do 9x plus x plus 2 already. F minus g of x. Here I want to warn you to be careful. F minus g of x would be f of x minus g of x. But just like any time we're doing a substitution right after subtraction, subtracting g of x means subtracting the entire g of x. That x plus 2 needs to be in parentheses. F of x is 9x. So we have 9x minus 2. F minus g of x would be 8x minus 2. F times g of x. Let's do that next. Fg of x would be f of x times g of x would be 9x times x plus 2 would be 9x squared plus 18x. We're distributing. None of this is new. This is classes old. What is new? The notation. I'm going to keep a note down here that fg of x worked out to be 9x squared plus 18x. Let's say we wanted to find fg of 2. Well, one way to do this, fg of 2, just like fg of x is f of x times g of x, fg of 2 would be f of 2 times g of 2. What's f of 2? Plug 2 into f. 9 times 2 would be 18. What's g of 2? Plug 2 into g. 2 plus 2 would be 4. And then 18 times 4 would be the same as 9 times 8. So it would be 72. Fg of 2 equals 72. Well, guess what? If we have the function fg of x, we can just plug 2 right into that. Fg of 2 would be 9 times 2 squared plus 18 times 2. That would be 9 times 4 plus 36, which would be 36 plus 36, which is, guess what? 72. So everything's working exactly like it should here when we do algebra with functions. Now, 9x and x plus 2, various different ways. Those work together well. Let's say our functions were a little more complicated. Let's say we had f of x equals the square root of 25 minus x squared. And let's say that g of x is just the number 5, constant function. Well, what would f plus g of x be? Well, that would be f of x plus g of x. It would be the square root of 25 minus x squared plus 5. And that's it. We can't combine that at all. The 5's not under the square root. We can't just take the square root of 25 when it's the square root of this expression. So that's as far as we can take it. That's the final answer. Square root of 25 minus x squared plus 5. Let's do some more. I'm going to pick some different functions. We're going to say m of x is 4x. We're going to say n of x is the absolute value of x minus 3. And we're going to say p of x is 1 over x plus 1. So 3. First, let's find, let me decap a bunch of these. What kind of markers would I like? Decap, please. Oh, sorry. Okay.
Let's find m minus, forget what I wrote, m minus n of 2. Well, what do we know? M minus n means m of the function, in this case, m of 2, or m of the function input, sorry, minus n of 2. Function m, that's 4 times our x, in this case 4 times 2, minus n is the absolute value of the thing minus 3. Here the thing is 2. That's not a 31, that's a 3 and end of our absolute value. Let's simplify. 4 times 2 is 8, minus the absolute value of 2 minus 3 would be the absolute value of negative 1. Absolute value of negative 1 is positive 1, so this is 8 minus positive 1. I've done something wrong. No, I haven't. This is correct. Next, let's do the same thing, m minus n, but instead of positive 2, let's go ahead and find m minus n of negative 2. So our next example, m minus n of negative 2. So that's m of negative 2 minus n of negative 2. M would be 4 times the thing. Thing is negative 2. Minus n of x minus 3 would be negative 2 minus 3. 4 times negative 2 is negative 8, minus the absolute value of negative 2 minus 3, absolute value of negative 5. The absolute value of negative 5 is positive 5, and negative 8 minus 5 is negative 13. Next up, let's do m times p of 1. Well, that's going to be m of 1 times p of 1. M of 1 would be 4 times 1 times p of 1 would be 1 over x plus 1, or x is 1. 4 times 1 is 4 times 1 over 1 plus 1 is 1 over 2. 4 times 1/2 is 2. So MP of 1, M times P of 1 is 2. For the one like this I'd like to do, I'm going to get rid of the number entirely. I'd like us to just find MP of X. Well, that's going to be M of X plus P of X. We don't have a different number to plug in, so it's just our basic definition. M of X times P of X. So that's 4X times, or sorry, I wrote plus there. This should just be times. Forgive me. Times M of X times P of X. 4X times 1 over X plus 1. Multiplying something by a fraction just multiplies it by the top. This is 4X over X plus 1. MP of X equals 4X over X plus 1, because that's 4X times this fraction. And by the way, MP of 1 would be 4 times 1 over 1 plus 1, which is 4 over 2, which is 2. Just like we got when we did it the long way. Next up, using these three functions, I want to do P over N of 3. P over N of 3. That would be P of 3 over N of 3. Well, what's P of 3? P of 3 would be 1 over 3 plus 1. What's N of 3? N of 3 would be the absolute value of 3 minus 3. So we could keep going and simplify the top, but we already got our answer. Top's 1/4. The bottom would be the absolute value, 3 minus 3. The absolute value of 0. So 1/4 divided by 0, that's undefined because we can't divide by 0. This meant the thing on the bottom was equal to 0. So remember, I said when we have the division one, we have to make sure the function on the bottom, in this case, N of X, isn't equal to 0. And when we specifically plug in 3, that's the value that makes N of X equal to 0. So it's the value that causes this to be undefined. I want to give 3 new functions. And g of x equals 2x h of x equals x squared minus 4x, and k of x equals the square root of x minus 1. These are the functions we're going to use to talk about determining domain of a resulting function. Okay, let's do g minus h of x. And we're going to write the domain of it in interval notation when we're done. So we need g of x minus h of x. That's going to be 2x minus x squared minus 4x. And what am I missing? What do I need? I need those parentheses because I'm subtracting the whole thing. The colors really showed why we need the parentheses there. We are subtracting all the orange, not just the x squared. If we simplify this, we have 2x minus x squared plus 4x. So we just have minus x squared and then 2x plus 4x plus 6x. So this would be g minus h of x. Now we also need to write the domain in interval notation. And the rule is going to be that we take the intersection of the domains that we started with. What does that mean? It means the overlap. The domain of g of x would be all real numbers. There's no restrictions. There's nothing we can't plug in. And remember, we find the domain by figuring out what we can't have. The domain is everything we can have. So it's easy just to pick out the things we can't and say everything else, that's the domain. Here, there's nothing to pull out because nothing makes this undefined. So everything is in the domain. Same with h. This is also all real numbers. So the domain of both is all real numbers. And that means the intersection, the overlap of those two intervals would also be all real numbers. Because there's nothing we can plug in that would make it undefined. And sure enough, if we look at this function, there's nothing that would make it undefined. Looking at the final function and determining its domain that way, we're going to see is not a good idea. Not a good idea, because it's going to give us some wrong answers sometimes. We have to take each of the starting domains into account. Let's do g times k now. So g k of x. That would be g of x times k of x. That would be 2x times the square root of x minus 1. Now, the domain of G, we already said that one's negative infinity to infinity. We've said the domain of H is also negative infinity to infinity. What about the domain of K? Well, the thing under a square root has to be greater than or equal to 0. Remember, we can't have negatives under the square root, not and still be in the real numbers. If I add 1 to both sides, x greater than or equal to positive 1, and in interval notation, that would be square bracket at 1 to infinity. If you don't remember how to do interval notation, there are review videos available to you from past classes from the front of the book material. You're going to want to look at, I believe it was section 1.4. That's the one where we talk about union and intersection of sets. We talk about interval notation. So find that union and intersection of sets video if you need to refresh on how to do interval notation. That's not a part of this class. That's in the prereq. You're expected to know it. But my old videos, well, they're new videos, but the old material is available to you. So we would need the intersection of the domains for G and K. Where do they overlap? Well, since that's everything, the overlap is just going to be the same as the domain there. So the domain for this function, our final answer of 2x radical x minus 1 is this. And that's saying that we only get an answer. The function is only defined for these values of x, for x is in that interval. Anything else would be undefined. Okay. Next one we're going to look at. Let's do k over h of x. That's going to be k of x over h of x. Now, making a function like this, k of x over h of x, we like that because that's easy. These things can interact with each other because the k is in the square root realm. The h is not. So after we put k over h, guess what we can do? Absolutely nothing. That is the final answer. I'm writing again so you see it in purple, but same exact thing. Now for the domain. The intersection is still this. But there are also going to be values that make the bottom 0. And we have to find those values because we're not allowed to have the bottom equal to 0. So x squared minus 4x can't be equal to 0. How do we solve quadratics like this? We factor. Again, that is old material. x minus 4 times x is what gives us x squared times, x squared minus 4x. So that means x equals 0 or x equals 4. I'll even write that out. X minus 4 equals 0, so x equals 4. Specifically, these were not equal, so they are restrictions that we can't have. The 0 we don't have to worry about because we already have the intersection, we already have the domain narrowed down to being 1 to infinity, including 1. 0's not in there anyway, so we don't have to worry about it. This 0's not already in there. It's already excluded by not being a part of the intersection. However, x equals 4, that is in the intersection. So we need to take it out. This is going to be including 1 to 4, not including 4. Union with 4 to infinity. So it's like I took this interval and I removed the number 4 so that it's still from 1 to infinity, but you can see this end and this start is specifically excluding the 4 value. So that would be the domain. We're given p of x is x squared plus 5x. And as much as I love color coding, I'm going to do this one in blue since it's the only marker that's not disappointing me right now. Q of x is the square root of 2 minus x. We want to find q over p of x, which we know means q of x over p of x. So we take our q, it goes on top. We take our p, it goes on the bottom. X squared plus 5x is p. Square root of 2 minus x is q. Q over p is literally putting q over p. Square root is only on the top. We need to find the domain of this, though. So what can't we have? Well, the domains of each of these, p itself, x squared plus 5x, there's nothing we can't have there. So the domain for p is all real numbers. For q, things under a radical have to be greater than or equal to 0. They can't be negative. So negative x would be greater than negative 2. Multiply or divide both sides by negative 1. Either way, that flips the inequality. X less than or equal to 2. So the domain for q is negative infinity to positive 2. But there is something else we have to consider besides just the domain of each of these. The bottom of the fraction can't be equal to 0. X squared plus 5x cannot be 0. How do we solve that? We factor. X times x plus 5 can't be 0, which means x can't be 0. X plus 5 can't be 0, so x can't be negative 5. So we're going to take the intersection of these two where they overlap, and that's just going to be this here. All real numbers and the real numbers up to and including 2 overlap as the numbers up to including 2. But we also have to rule out x equals 0. And we also have to rule out x equals -5. So what does that give us? It gives us -infinity to -5. Rule out -5. So union, there we go. Then we keep going, -5 up to, but not including 0 because we're taking out 0. And then we can go all the way up to 2 and include 2, but this will be the domain. Why is it important to figure that out? Because it's not enough to know this part. The question said, find the function and write the domain in interval notation.
Well, if we let f and g be two functions, the sum is f plus g, the difference is f minus g, the product is f times g, and the quotient is f divided by g. And they're all functions whose domains are the set of real numbers common to the domains of f and g. So we take their domains, and where the domains overlap, that's the domain of the sum, difference, product, or quotient. F plus g is just f of x plus g of x. F minus g is just f of x minus g of x. F times g is just f of x times g of x. And f divided by g is f of x divided by g of x, where of course g of x can't be equal to 0 because we can't divide by 0. So let's let f of x equal x minus 5 and fix that g of x equals x squared minus 1. Find f plus g of x and then determine the domain of the function. Well, f plus g of x is just f of x plus g of x. So we're adding x minus 5 and x squared minus 1. That's just the single x squared, the single x, and then -5 minus 1 is -6. X squared plus x minus 6. The domain of f has no restrictions. The domain of g has no restrictions. That is, we can plug in negatives, we can plug in 0, and we can plug in positives. So the domain of the sum has no restrictions. It's going to be -infinity to infinity. The composition of the function f with g is denoted as f composite g. That circle, f circle g, that's not a multiplication dot, and is defined by the equation f composite g of x is f of x. Sorry, it's f of g of x. So f composite g is f of g. The letters stay in the same order. So g composite f would be g of f of x. So pay attention to the order that you're asked to take the composition in, because F composite G and G composite F are not the same thing. The domain of the composite function f composite G is the set of all x such that x is in the domain of G and G of x is in the domain of f. That makes sense. In order to get in this function, you have to be able to be plugged into G. You have to be in the domain of G if you're x. And then in order to be plugged into the function f, G of x needs to be in the domain of f.
Now we're going to talk about F circle G. That's not an O. That's a little circle. F circle G of X, keep the letters in the same order, means F of G of X. We're taking one function and we are plugging that function in to the other one. This is called composing functions. When we talk about composing functions or function composition, we're talking about taking a function and plugging it into another function. So this means that G of X is inside of F. If we had G circle F, G composite F of X, the order tells us what to do. G of F of X, which means F of X ends up inside of G of X. And the colors are going to be real useful on these examples. Let's take a look at f of x equals x squared plus 2x. And g of x equals x minus 4. Let's take a look at f composite g of x. Well, that's equal, keeping the order the same, to f of g of x. F composite g of x is f of g of x. How do we do this? Well, we know what g of x is. G of x is x minus 4. So let's make that replacement. F of x minus 4. And f is this function up here. Something squared plus 2 times that thing. And what is that thing going to be? It's going to be x minus 4. That's what we're plugging in. So just like we did with the difference quotient work, x minus 4 squared, that's going to be x squared minus 8x plus 16. That's just this part. Plus this stuff, plus 2x minus 8. That's that part there. And now we combine our like terms. to get our final answer. X squared minus 8x plus 2x is minus 6x. Plus 16 minus 8, that's plus 8. X squared minus 6x plus 8. What if we wanted to find F composite G of 2? Well, if we have F composite G of X, we can plug it in. 2 squared minus 6 times 2 plus 8. 4 minus 12 plus 8. 4 minus 12 is negative 8 plus 8. I think I screwed up somewhere. Well, no, I'm good. I keep thinking that I'm screwing up and I'm not, because I keep changing the examples, forgetting that I changed them. Then I look at the book and I see that didn't match up. No, we plug 2 in. F composite G of 2 is 0. Well, what if we didn't have this function? And what if we needed to find F of G of 2, but we didn't want to go ahead and find the composite function, if we just wanted to skip here? Well, F composite G, or as I might as well just read it, F of G of 2. That's F of G of 2. What is G of 2? We can find that easily by plugging 2 into G. That's 2 minus 4. So we're looking for F 2 minus 4 is negative 2. F of negative 2 would be the thing squared plus 2 times the thing being negative 2. Negative 2 squared is 4. Plus 2 times negative 2, that's minus 4. And we get 0 that way as well. And I feel better about thinking that I'm wrong, because I did it 2 ways. I got the same answer both times. I know I'm right. Let's do something different this time. Let's take a look at G composite F of negative 5. I'll do them in the reverse order this time. I'm still going to show both ways. G composite F of 5 would be G of F of 5. G of f of negative 5. There we go. Order stays the same. G composite f, G of f, G of f of negative 5. This is going to be G of whatever it is when we find f of negative 5. That's the thing squared plus 2 times the thing. The thing is negative 5. That's G of negative 5 squared is 25 minus 10. So we're looking for G of 15. And that's going to be the thing minus 4. Here the thing is 15. And 15 minus 4 gives us 11. Which is right. I didn't change that one. Now, how can we get that same answer of 11, but without dealing with the numbers? Well, before we plug in x equals negative 5 to get our answer, we can find G of f of just x. G of f of x. G of what is f of x? X squared plus 2x. Now we're plugging that into G. That's going to be the thing minus 4. The thing is x squared plus 2x. So our function is x squared plus 2x minus 4. That's G of f of x, or G composite f of x. If I plug negative 5 in, I get negative 5 squared plus 2 times negative 5 minus 4. I get 25 minus 10 minus 4. I get 15 minus 4, which is 11. F of x equals x squared plus 2x. G of x equals 3x minus 4. We want to find f composite g of negative 2. So f composite g of negative 2, keep the letters in the same order, means f of g of negative 2. So what's g of negative 2? Plug negative 2 in for g. 3 times negative 2 minus 4. That's negative 6 minus 4. That's negative 10. So what are we looking for? We're looking for f of negative 10. And how do we find that? We plug it in. Negative 10 squared plus 2 times negative 10. F and g, x squared plus 2x, 3x minus 4. F composite g of negative 2, keep the letters in the same order, means f of g of negative 2. G of negative 2 we found to be negative 10 by plugging negative 2 into g. So now we see we're looking for f of negative 10. We're finding that now. X squared plus 2x, negative 10 squared plus 2 times negative 10. That's positive 100 plus negative 20. 100 minus 20 is positive 80. And positive 80 is our answer. Let's say we had a function h of x equals the absolute value of 2x squared minus 5. Now, for once, we're not going to try to graph this. We're not going to move something up, down, left, right. But what we are going to do here is find f of x and g of x such that h of x equals f composite g of x. Now, the way we're going to approach this is first, we're going to rewrite this composition the way that it makes sense to us. Instead of f composite g, we're going to write h of x equals, keep the letters the same order, f of g of x. Now, what we see is that g of x is inside of f of x. So g of x here is going to be our inside function. And that means f of x is going to be what we call the outside function. So why do we call g of x the inside function? Because when we write f composite g of f as f of g of x is on the inside. Now let's look at what we have for h of x. What is on the inside of something up here? Well, 2x squared minus 5 is on the inside. So g of x must be 2x squared minus 5. On the inside of what? F of x will be the outside function. What g of x is on the inside of? And what is g of x inside of? It's inside of an absolute value. So f of x must be the absolute value of x. We can check here by composing. Let's make sure what we picked is correct. We wanted it to be f composite g, or f of g of x. That's going to be f of what is g of x. We picked 2x squared minus 5. Putting that inside of the function f means putting it inside absolute values. So absolute value of 2x squared minus 5, that is our h of x. So we picked the correct f and g, the correct inside and outside function. Let's do another. Let's say we have the function m of x and it equals the cube root of 5x plus 1. This time, let's find G composite f of x. So G composite f is the same as G of f of x. So this time, f of x is going to be inside of what? G of x will be the outside. So looking at our function m, what is inside of something here? 5x plus 1 is inside of something. So the inside function, f of x, must be 5x plus 1. And it's inside of what? It's going to be inside the outside function. It's inside this cube root. So cube root of x must be g. And if we wanted to check, g of f of x would be g of 5x plus 1, which would be a 5x plus 1 inside of the cube root. It is the function that we were decomposing. So we did pick the proper inside and outside functions. Okay. That wasn't so bad. We're given h of x equals x plus 7 cubed. We're told that we want h of x to be f composite g of x, and we're supposed to find what f and g are. F composite g means f of g of x, which means g of x is our inside function and f of x is our outside function. What is on the inside here? What's going to be g of x? Well, the thing on the inside is x plus 7. And what is it on the inside of? It's on the inside of the outside. It's on the inside of x cubed. That's it. That's the thought process. So f of x is x cubed and g of x is x plus 7. X cubed for f, x plus 7 for g. It can't be the other way around.